In this video, we will be looking at another approach toward the alkylation of enolates. This is the malonic ester synthesis. The malonic ester synthesis, similar to the acetoacetic ester synthesis, involves alkylation followed by saponification and then decarboxylation. The difference between them is based on the starting material. Whereas the acetoacetic ester synthesis started with a beta keto ester, here we are starting with a beta diester. So this dicarboxylic acid is called malonic acid, and so we have the diester of malonic acid as our starting material. When this is treated with a strong base, we are using the methoxy because that matches the ester. So the methoxy can grab off one of these protons, which generates this enolate. This enolate can now act as a nucleophile in an SN2 substitution. So this can share its electrons with this carbon, pushing away iodine as the leaving group. Giving us this product. So we have alkylated the position in between both esters. Next, both esters can be hydrolyzed, so saponification would give the carboxylate, and then aqueous acid workup would protonate the carboxylates to give the carboxylic acid, and that will give us the following. We now have a beta diacid. When this is heated, this can undergo decarboxylation. Leading to this product. Oops, I forgot we get one more hydrogen back here. So we lose carbon dioxide, and so we can imagine that this hydrogen ends up back here again. So with the malonic ester synthesis, we are taking advantage of the ability to alkylate in between two carbonyls, but then we are getting rid of one of the carboxylic acids at the end. So our final product, it's as if we have alkylated acetic acid. So here we have a summary, and starting out with our diester. This is deprotonated to form the enolate, and then SN2 substitution will give an alkylation product. Hydrolysis of the ester followed by decarboxylation gives us this product. Remember, this came from the alkyl group, and then this piece is what's left from the malonic ester. Thinking of it from the perspective of the alkyl halide, our R group is connected to basically to the alpha position of acetic acid. Now, when we talked about the acetoacetic ester synthesis, for certain target compounds, we potentially could have done direct alkylation rather than doing the acetoacetic ester synthesis. The net result of the acetoacetic ester synthesis is it's as if you started out with this and you converted it to this with some new R prime. In the case of the malonic ester synthesis, it's as if you are using acetic acid and converting this to something like this. But obviously you couldn't just treat this with base and try to form the enolate, because the base would just grab off this proton. Alright, so the malonic ester synthesis gives us an approach to make this type of compound using a starting material that is a substitute for this. Let's look at an extension of the malonic ester synthesis. So rather than alkylation, saponification, decarboxylation, we could do a dialkylation. So starting out with a malonic ester, we can alkylate once, for example, with ethyl iodide, and then we can alkylate a second time, for example, with methyl iodide. Let's take a look at this. Methoxide will deprotonate here to form the enolate. I'm not showing all of the intermediates. I encourage you to write those out, but we're going to go through a little bit more quickly. This enolate will do SN2 substitution, kicking out the iodide as a leaving group. So at the end of the first arrow, this is the product we would have. Another equivalent of methoxide could grab off this proton, generating an enolate that could add here, kick away iodide as the leaving group. Giving us this product. Hydrolysis of both esters, followed by decarboxylation, will give us this product. So once again, it's as if we had acetic acid and we replaced two hydrogens with two different alkyl groups. So the malonic ester synthesis is a way to make a target compound that could be seen as a substituted acetic acid. Whether it is a single alkylation or a dialkylation, malonic ester synthesis can be very useful. We could consider another extension using other beta diesters, but the only other version would have an extra alkyl group here, and so that would be similar to already having one alkylation having occurred. So nothing else can be gained by using other beta diesters, but the possibility of a single alkylation or a dialkylation makes the malonic ester synthesis an effective way to synthesize particular types of carboxylic acids.